I don't have the quiz. If you have time after class, you can come down to my office.
I don't see any. I said it too soon.
Okay, it's 1 o'clock. You ready?
Sure.
Did everybody have a good Halloween?
Yeah, physics test is last.
Who does that? All right, well, I'll start with a congratulations. You're here, so you've made it to chapter 8. That's a good thing. Actually, I believe it's called sequences and series. I'm not going to say hardest. Here's what I will say. Students usually find this to be slightly uncomfortable because it is going to be very different than anything that you've seen. So there's new notation, there's new language. And yes, we will be doing some derivatives. Yes, we will be doing some integration. But otherwise, the topic is pretty much its own thing. All right? So let me try and motivate the idea with an example. Okay? There's a lot going on in this chapter. But let me just try and show you a place that we might want to get to at some point. Let's say we try and take this antiderivative of e to the negative x squared. That's a very famous integral. And we can sit here and we can take all sorts of tries at, u substitution. We might try an integration by parts. All these different techniques that we have, none of them are going to work. And I may have mentioned this to you before, that in the real world, if we take all functions and put them into a bucket and just kind of randomly pick one out, and put it up there and trying to integrate it, the chances that we can integrate it using u substitution or any of the methods that we've learned is essentially zero. So most functions cannot be integrated in an exact form using some method. So there were two fathers of calculus. It means there are two people who developed calculus, Isaac Newton and a guy named Leibniz. And it's kind of amazing if you look back at the history of it, because they developed calculus independently, which means they didn't know of each other's existence, and they did it about the same time. So Newton was developing calculus, and Leibniz was. And so people argue, who's the real father of calculus? And I think they both get credit. But Newton had something that Leibniz didn't have, all right? Newton dabbled in this whole thing with series where Leibniz was not involved with that. So if you gave this integral to Leibniz, he would just wave his hands at it and be like, I don't know. But if you gave it to Newton, he could do it. And so that's what I want to try and get us to, is to the point where we can do this integral. All right? But it's going to take a lot of work to get us there. All right? We have to develop an entire kind of new way of looking at things. All right? So we're going to start with 8.1, and let me kind of reiterate what I just said. This chapter has a lot of things. That integral I put up there is a goal, right? But it is not the only thing we can do, all right? There's a lot of things we can do with sequences and series, but that's one thing that can be done, all right? So let's start out with sequences. So what is a sequence? When you think of the word sequence, what do you think of? Do you think of anything? One thing after another? Yeah, like a sequence? Okay, that's exactly what it is. One very general definition for this is that it's just simply a list of numbers. Now, we're going to see here in a second, or as we move through this chapter, that it doesn't have to be numbers. A sequence can be a list of any object. It can be numbers, it can be functions, it can be integrals, it can be any list of things is a sequence. But we're going to start by looking at a list of numbers. So let's just start listing out some numbers. Or let's write some examples of lists of numbers. So here's one. 1, 2, 3, 4, 5. Okay, that is a sequence of numbers, right? We're not going to overcomplicate this. That's a sequence of numbers, right? We call this a finite sequence. Finite because it starts and it stops, right? Okay, let's compare that to this sequence of numbers. And I put 3 dots at the end. So what do you think that those 3 dots really mean? That this continues, right? And it never stops, but it maintains the pattern. So the next number we could assume would be 5, right? And then the one after that would be 6. And that's what's happening here, right? That's called an infinite sequence. Finite sequence. Now, when we write sequences of numbers, the standard notation is to put the sequence in a set of braces like this, right? So I didn't do that initially, but now I'm going to. So you put a brace around here, you put a brace after the dots. Now, this particular sequence is a famous one. It's the one you learn when you're a kid, right? They're the counting numbers. So this is actually the sequence that we call the natural numbers. So you've seen this before, real numbers, all the real numbers. But if you do this is called double struck, a double struck capital R, double struck N. This is the natural numbers. And these were the first numbers that human beings actually started using. 1, 2, 3, right? I'm going to give you 3 sheep. You give me 5 barrels of whatever. You right? Or you know what I'm saying? Bushels of corn, whatever. We started trading things, and so these were the first numbers that we started with. Then we introduced the other numbers. All right. Okay, so we're going to take a slightly different perspective on these now. I want us to now look at the idea of a sequence as a function. Now, we've dealt with functions already, right? And all the functions that we've normally dealt with in this class, you would plug in a number into the function and it spits out a number, right? Plug in a number, spits out a number. The number that we plug in has usually been able to be any real number, right? So like, for example, an example of a function that we've dealt with, x squared, right? Something like that. So you give me a number, I can square it. And the number you plug in could be 1, 2, but it could also be like 0.5, 0.3, right? So when we look at a function like this in the past, what we would say is that this is a function that goes from real numbers to real numbers. So the input, okay, this is the x, this is the input in, and what comes out is a real number. Real number in, real number out, okay? I want us to now look at this idea of a sequence as a function that goes from the natural numbers to the real numbers. Now this is important. What we're saying is that for sequences, you're going to plug into it one of those counting numbers. And that's all you can plug in. You're only allowed to plug in 1, 2, 3, 4, 5, 6. You can't plug in fractions, you can't plug in pi, you can't. So we're eliminating a bunch of numbers, aren't we? But what comes out of it is going to be a real number. Okay? Is that okay? We're going to do some examples, but this is the idea. Input has to be a natural number. The output can be a real number. That is how we want to view a sequence. So let's go back and look at this example again. Let's do this example. Let's take that infinite sequence, 1, 2, 3, 4, ... that goes forever, right? All right, can somebody tell me what the function is if I tell you that these are the outputs? Outputs. These are the outputs right here. So you think the function is like f of x equals x? That's what I heard. Someone said x, yes? So let's see if that's true. If f of x equals x, then what would f of 1 be? 1, and then f of 2 would be 2, right? F of 3 would be 3, and so on and so forth. So if I just show you the outputs, and I'm telling you that the inputs have to be just the natural numbers, then here's your inputs, right? 1, 2, 3, and the outputs are exactly the same thing. So it looks like, yes, this would work, right? You know, kind of seeing this? This is such a simple example. Sometimes simple examples are confusing. Now, x for us in the past has always represented a real number though, right? So I need some way of letting you know that I'm not talking about our traditional function. So what I do instead of this is I define my function f to be f of n. And I define it to be n. So f of n is n. Now the reason I'm using n is to let you know that I'm talking about natural numbers as the input, as opposed to x, which would make you think real numbers can go in. Does that make sense? You sure? Okay. And we look at that for a little while and we go, you know what? We can use even a different notation. Why don't we scrap this and we use this notation? A sub n equals n. Now, just look at it for a second and then we'll talk about it. It's like I've replaced the f with a, and I've replaced this n, or I've just moved it down to a subscript instead of inside like a parentheses. So if I use this notation, then what would a sub 1 be? Well, a sub 1 is, in this particular case, 1, right? And then a sub 2 is 2, and a sub 3 is 3, and so on and so forth, right? So do you see that with this notation, this first number is a sub 1, the second one is a sub 2, this third one is a sub 3, and so on and so forth? Yep. So I'm just trying to clarify some notation right now and get you to see that the input's a natural number, the output is going to be some real number. Are y'all ready to look at a different sequence? Because this is a pretty boring sequence. Okay, let's start a new one. Between what? Natural numbers and rational? Well, real? The natural numbers are just the integers 1, 2, 3, 4, 5 forever. Real numbers include all the stuff in between. So like you can have like 0.75 or, you know, square root of 2. There's a bunch of numbers that are not integers. So if you look at it like a number line, here, I can do it this way. If this was the first thing I did when I walked into class today, is I said, hey everyone, I want you to sketch the function f of x equals x. Then I think everybody here would, whoa. Yeah. Everybody here would be comfortable with the idea that that's just this diagonal line, right? So like if I plug in 1, it spits out 1. If I plug in 0.5, it spits out 0.5. Plug in -1, spits out -1, right? But if I ask us to look at this instead, the sequence a sub n equals n, then you're only allowed to plug in what? 1, 2, 3, 4. So if I plug in 1, what do I get? 1. It's a dot, isn't it? If I plug in 2, I get 2. I plug in 3, I get 3, 4, 5. So the difference between the function that takes real numbers in and spits real numbers out is that it creates a solid line, doesn't it? But the sequence, a sub n equals n, creates a sequence of dots, doesn't it? And there's nothing in between them. Does that make sense? All right. Okay. So let's try a new sequence. Let's see if you can come up with this sequence. Okay, my question to you is, what is the function that would spit out that sequence? 2x, but we're not going to use x. We're going to use n. 2n, right? Now think about this. This has to be a sub 1, right? This one has to be a sub 2. This one has to be a sub 3. This one has to be a sub 4, and so on and so forth. So that means when I plug in 1, it needs to spit out 2. When I plug in 2, it needs to spit out 4. When I plug in 3, 6, 4, 8, right? Those are just doubling, right? We're just doubling the input. So a sub n is 2n. Right? That creates a sequence, an infinite sequence of even numbers. Let's do another one. How about this one? So this has to be a sub 1. This has to be a sub 2. This has to be a sub 3. And you know what? I probably should have done this. You should put a big, huge star next to this one, because that's a very important one. I think it's obvious, like it's an easy sequence, like 2n gives you even numbers, 2, 4, 6, 8, 10, right? But it's used a lot. We're going to be using that sequence a whole lot. And we're actually going to use it right here. So when you look at this sequence, what do all these numbers kind of have in common? They keep increasing by 2, right? So this is kind of like the even numbers, isn't it? But yeah, it's almost like what we did is we took this sequence and we kind of shifted it. So I can start, instead of starting at 2, I'd like to start where? At -4. So if I just took this and subtracted, how much from it? What do I have to subtract from this to start here? 6, right? Now what would happen if I subtract 6 from this? Look at that. Subtract 6 from that. That. Right? So couldn't I use the same sequence over here, but then just subtract 6? And that would just imagine just taking this whole sequence and just like translating it, shifting it over 6 units. And that would spit out that sequence up there, wouldn't it? And you can always check it, right? That's a good thing. You can always check it. A sub 1, you plug 1 in here. 2 times 1 is 2. Take away 6, you're at -4. So that's this one. And then how do I know they're going to keep going up by 2? Well, because I'm using 2n, right? That keeps jumping by 2. All right, what about this? What do you think about this one? What do they keep jumping by? 3, 3, 3, 3. So instead of using 2n, I should probably use 3n, right? Okay, so 3n is going to help me jump by 3 each time. But if I plug 1 in here, I actually get 3, and I don't want that, right? If I plug 1 in, I want to get -3. So what do I have to do to that to make that happen? Subtract 6 again, right? It's not always 6, that's the way I wrote the sequence, okay? And that should work. So you can check the first few. Are y'all seeing that? Okay. Try this one. Ah, what happened? Come on, Robert. Stop it. That's why I do them so fast. I cannot do one right now. Hold on. I need to think about something else. What is going on? I'm having like a major malfunction up here. All right, I don't even care anymore. Okay, let's do this one. Let's do this one. 1, 3, 5, 7, 9. All right, there we go.
They're like getting...
Yeah, they're getting worse. All right, what are these? These are actually another important, this is actually another important sequence that's going to come up quite a bit. They're not, oh, wait, no, they're not prime. 9's not prime. One, 3, 5, 7, 9. Are they jumping by the same amount each time? Yeah, okay. Those are odd numbers, aren't they? So, yeah, the way we can look at this is if we look back at what the evens were, right? Evens were 2, 4, 6, 8, 10. The odds are always just going to be one less than that. So if we use this sequence, 2n, that would generate the evens, right? Starting at 2, but I want to start at 1. So if I take away 1, then I'm going to get 1 first. Then when I plug in 2, I get 4 minus 1, which will give me 3. And then when I plug in 3, I'm going to get 6 minus 1, which will give me 5. See how that works? Can you see already that when we start talking about sequences in the series, it's hard to teach someone how to see a pattern? It's just some people, like, they just see it, and others, it's really difficult for them to see it. Okay, let's try this one.
Yay.
All right, thank you. That was even better.
That way you got it back.
Yeah. Normally in textbooks they use 3 dots. Sometimes I'll do 2, sometimes I'll do 4 or 6, or it just depends on how many I feel like doing, all right? But most books use 3 to represent continue. All right? Do you recognize that those are odds? You can also say they go up by 2, right? They just keep increasing by 2. So if I'm going to start with 1, if I plug 1 in there, I'm going to get 2, but I need to be at where? 7. So if I add 5 to that, then if I plug in 1, I get 7. If I plug in 2, let's just check real quick. Get 4 plus 5 is 9. Plug in 3, I get 6 plus 5 is 11, right? So you can create a whole lot of sequences from just the idea of like even and odd, jumping by 2. All right, let me make sure, I'm just making sure I cover all the things I want to talk about here before I move on. Come on, man. Okay. Some other notation. Other notations. Okay. Let's say I think with these notations, I'm going to give you some examples to help you see this. Let's say I take this sequence, let's do the 2, 4, 6, 8. Let's just take that sequence of even numbers. That is one way I could write it, okay? Another way I could write it is a sub n equals 2n, right? Which I already showed you, yes? But there's a couple of other notations I could use. Another notation is I could just write 2n with the set of braces around that, like that. This and this and this are all the same thing, all right? So these are all equivalent notations. Here's another notation. Do you understand that notation? Yeah, this one's actually being very clear with you that we want to start at 1 and never stop. Here we don't say that, right? So it's implied. It's kind of like when we do square roots, right? Square root of x. We understand that there's a 2 out here. If we don't write anything here, it's understood that it goes from 1 to infinity. But sometimes we don't want to start at 1. So we'll use this notation and I'll put like maybe n equals 4 to infinity, and then that changes the sequence a little bit, all right? So this notation allows us to change our starting point if we wish to, all right? Let me see. Yeah, that's about all the notations that we'll see, okay? Do all sequences go to infinity? Do you mean that these numbers are getting bigger and bigger and bigger and bigger?
Yeah, like the 3 dots, they always have to
Oh, do all sequences have to keep going forever? No, because we could have a finite sequence, which means I would stop it somewhere. Let me give you an example.
Oh, yeah, I saw that.
Right? What about this one?
You think too much about it while you're
It's because
doing
people
it.
are laughing at me while I'm doing it.
I'm only laughing because you stop for like a long period of time.
Sorry, that should not be n equals on top. 100. There we go. Is that an infinite sequence or a finite sequence? It's a finite sequence.
Do you have a sequence that goes to negative infinity?
Well, the numbers we're plugging in are natural numbers, not negative numbers, right? So I think what you're asking is, could this go to negative infinity up here? That would imply that we're plugging negatives in, right? And the whole idea behind the sequence is that our input is a natural number, 1, 2, 3. So we wouldn't ever do that. And that's because we want to talk about like what's the first one, what's the second one. So if this is our input, we would never want to say like what's our negative one, negative 2. You know what I'm saying? Okay. So if I were to write this sequence out, what would my first number be in that sequence? 6, right? And then the next one, 8, and then 10, and then this would continue, right? But it would stop. So where would it stop? At 200. So that is a finite sequence. I'm not sure if that addresses your question. You asked, does it always have to go to infinity? No, it doesn't. We can have a finite sequence like this. Okay? But we are going to study almost exclusively here in this chapter infinite sequences. Now, when you first asked me that question, I thought you were asking me something else. I thought you were asking me if when you do a sequence, if the numbers have to go to infinity. Like, see how these numbers are getting bigger? I thought you were asking me, does that always have to happen that they get bigger? That's what I thought you were saying. So let's answer that question, even though that's not what you were asking. Okay, what about this sequence right here? Those numbers are getting smaller, aren't they? Let's see if we can't come up with a formula for this. And here's the point where I start to recommend that you not try and make this more complicated than it is. When you look at this, if you see fractions in your sequence, like this, what I'd like for you to consider is the numerator and denominator separately. All right? Look at your numerator and denominators. Does your numerator ever change? Your numerator is always 1, right? Okay. So in my sequence, I know that all my numerators are always 1. Now, what can you tell me about the denominators? They keep going up by 2, and they start where? My first denominator is actually 1, right? So it goes 1, 3, 5, 7, 9. Those are odd numbers, right? Didn't we already have a formula for odd numbers? What was it? 2n minus 1, right? So that would generate that sequence right there. You with me? Okay. How about this? How about this? 1/3, 1/5, 1/7. So I just changed it just a little bit. I'm starting at 1/3 instead of 1. Same pattern, right? The top never changes. It's always 1. The bottom, odd numbers, right? But starting where? Starting at 3, right? So what would I need to do to make that happen? 2n plus 1, right? 2n minus 1 gives you odd numbers, but this starts at 1. We want to start at 3, so we want to add 2 to this formula, which would give us this. Still good? Okay.
I know, I've seen those like tricky questions on like social media that tell you, oh, find the pattern, and it gives you like 1. I'm not sure if that's like a good example. 1, 5, and then like 11, 2. Like,
Yeah.
is that an actual thing?
Yeah. I mean, that's kind of what we're doing right now, right? We're finding a pattern, and we're expressing it as a function. Now, we are assuming that the pattern continues. Like, there's nothing that tells me for sure that the next number is 1/11. But if I assume that this pattern continues, then this would be the sequence for it, right?
Do you think we're going to get to the point where there's like a sequence that changes? Does that make sense?
Yeah. No, our whole goal is going to be to try and come up with a formula that covers every possible. Like, it's going to, even if our sequence does something weird, our formula will cover that. All right. Let me give you an example. Another one. Okay. So how about this? How about 3/8? Okay. 1/2. 7/12. 9/14.
You'll have to do one for the numerator and one for the denominator.
Like different formulas, one for the top and for the bottom. Looks like we might need that, yeah. Okay, so you can't rearrange the order, okay? The order is the order. So let me help. Okay, there. Now. Is there anything that's kind of messing you up, or that's the 1/2 is bothering you? Oh, 1/2 is really 5/10. Oh, it is. Yeah, it is. But I would have never written 5/10 because 5/10 reduces to be 1/2, right? So this is actually 5/10. Now look at your numerator and denominators. What is your numerator doing? 3, 5, 7, 9. Those are odds, right? Starting at 3. What are your denominators doing? 8, 10, 12, 14. Even numbers starting at 8. So let's try and create the numerator first. It's odds, so I know I've got to jump by 2. I want to start at 3, don't I? So this plus 1. And then the denominator is evens, but starting at 8. So I know I need 2n, but I need to start at 8. So how much do I need to add to that? 6. There we go. Got it? Now I do a perfect one.
I look away every time you do them now because I feel like
You feel bad. You should feel bad.
I feel like I did almost.
What do you see? Top is 2n minus 1. Everyone agree with that? We've got odds up top. Okay, I can buy that. All right, denominators. They're not evens, are they? I mean, they are even numbers, but they're not like 2, 4, 6, 8, 10. But they're doubling each time. Ah, so this is, you could look at 2 as being 2 to the first power. You can look at that as being 2 squared. You can look at that as being 2 cubed. This one's 2 to the fourth, right?
Yeah.
So the thing that keeps changing as we move down the sequence is that this power keeps changing, right? So when we plug in 1, right, this is a sub 1. So when we plug in 1, we want the 1 there. If we do a sub 2, we want the 2 there. So it should just be on the bottom what? 2 raised to the n. Not 2 times n, 2 raised to the n. So these are all powers of 2 down here. This has a name. This is called an alternating sequence. And we call it alternating because it keeps alternating in sign. Negative, positive, negative, positive, negative, positive, negative, positive. So how in the heck are we going to make that happen? So a sub n, I already heard it. What is it? Negative 1 to the n. That'd work, right? If we plug 1 into this, right, to get our first one, when we plug in 1, we should get negative 1 to the first power, which is negative 1. But when we plug in 2, negative 1 squared is positive 1. And then when we plug in 3, negative 1 cubed is negative 1. So we go back to negative 1. Then to the fourth power, back to 1. And you see, it'll just keep switching. Very, very useful for us to have a way of making our sequence alternate. Now, what if you didn't want it that way? What if you wanted it the other way? You wanted to start with positive and then go negative, then positive, then negative. How could you adapt your formula? Do what? Negative 1. So you're right, but let me just, wouldn't we just take each of these and multiply each of those by negative 1? Yeah. So I could use that formula, but then just take all those answers and multiply by negative 1. And that would change their signs again for me, wouldn't it? Yeah. So like that right there would create this, but then multiplying by negative 1 would switch that to a positive 1, then that to a negative, then that to a positive, right? But these have the same base, don't they? And this has a 1 here. So if you have two bases that are the same, you add the exponents. Negative 1 to the n plus 1 would work. Both of those are important. Okay, try this one. Let's see. Hold on. That's a 0.
Okay, just making sure.
Yeah, sorry. Okay, yeah, we'll just do this. Right, so now when we look at this, we have an alternating sequence, don't we? It's going, is 0 positive or negative? It's neither. But it's even, right? So if we ignore the signs, this is just even numbers starting where? At 0. So how can I make that happen? We'll deal with the signs in a second. The even numbers, I'd need to subtract what? 2. And that would give me my even numbers starting at 0, wouldn't it? But then I needed to switch signs. I needed to go like positive, negative, positive, negative. So how do I make that happen? This one right here, right? Positive, negative, this one. So all I have to do is multiply that by -1 to the n plus 1. And that would create that sequence. We could check it, right? Wait, hold on. It was positive, negative. Yeah. So if we plug in, wait a minute, hold on a second. -1, 1, 2, 1. We get 0. Is this working?
Yeah.
Yeah, it says if you
So if we plug in 1, what do we get here? We get 2 here, right? So that's going to be positive, but that's going to be 0. Okay. Then we plug in 2. 2 plus 1 is 3. -1 to the third power is negative, right? So that's negative. We plugged in 2 here, and we got 4 and then 2. So yes, that'll work. Now you might be asking yourself, is this formula that we come up with unique? Like, is there only one formula for a sequence? Like, could somebody else come up with another formula that creates the same sequence? And the answer is yes. These are not unique. Someone else could come up with something else that would still create that. And that's important because we might get answers that look a little different than what the book has if we're checking our answer, but it may still generate the same sequence. So the only way to do it is just kind of check and see. All right, let's try.
So like on the test, you would have to check each one of them.
You would have to check each one of them?
No, like you grading them.
Yeah, I'd have to make sure that it works, I guess, yeah. Yeah.
That's good.
Yeah, I mean, normally I can look at it and tell if it's doing what it's supposed to do. All right, sorry, I've got like this weird headache today. I'm not sure what's going on. It's messing up my ability to draw braces, apparently. Yeah. Okay, let's do one more. I think maybe one more. Negative 2/3, and then how about 4/9, -8/27, ... That's all I'm giving you. So the approach that I like is to first figure out, is it an alternating sequence? Yes, okay, and it starts negative, then positive, then negative, positive, right? So how do I create that? -1 to the n. To the n. N plus 1 will start you at positive, okay? N will start you at negative, which is what we want. Now, take a look at the numbers. So you can ignore the signs now, right? Ignore these signs? Okay, if we ignore those signs, let's look at those fractions. Do you see anything on top? It's 2 to the n, right? That's not even numbers, that's 2 to the n. And then what about the denominators? There's 3 to the n, right? This is 3 to the first power, 3 squared, 3 cubed. So this is 3 to the n. Now both the 2 and the 3 are to the n, aren't they? So I could, if I wanted to, write this as -1 to the n times 2/3 to the n, right? And even more, since these are both raised to the n and they're being multiplied, I could write that as negative 2/3 to the n. So I could put the negative together with the 2/3 because they're both to the same power.
So you don't care how we write it like on a test?
I don't care. Yep, as long as it's right, I don't care. Like, I'd be happy with this. But please understand, you should be comfortable getting to here because you're going to need to anyway in a little while. All right. I think that's good enough for at least getting you introduced to the idea that if I give you a sequence, or if we're given a sequence, we can try and generate some formula for it, right? One last one, sorry. Ah! That's like, that went backwards. Trying too hard. I'm not going to let you sit here too long on this one because you're not going to come up with a formula. All right, it's not going to happen. There is one, but it's way too complicated. So this is a famous sequence. Has anyone ever seen this sequence before? Has a name? No? Fibonacci sequence. It's called the Fibonacci sequence. Yeah, there's something, it's like a perfect, something about it, perfect, whatever. So let me show you how the sequence, so every sequence we've done up to this point is what we call an explicit sequence, meaning I can give you the formula for it, right? Like, here's the formula, bam, right? If you want to know, like, let's say we do n squared, okay? Like, let's say that's our sequence. Then if I wanted to know the eighth number in that sequence, I just plug 8 in, I would get, what, 64? And if I wanted to know the 1,000th one, I would just plug 1,000 in. That's explicit. The formula is there. The Fibonacci sequence cannot be, well, it can be written explicitly, but it's very complicated, like I said. So this is what we call a recursive sequence, which means that it has a definition, and you can get the numbers in the sequence, but you can't just go out and grab one from way down the line. Like here I could grab the 8th one, the 1,000th one, just real easy by plugging in. Here I can't. So what is the pattern in the Fibonacci sequence? Well, let me tell you what it is. Here's the definition. First of all, the first number of the Fibonacci sequence is given to you. I'm telling you it's 1, okay? The second number in the Fibonacci sequence is also 1. I'm telling you that. I'm giving you that, okay? Now, here's the rule. A sub n plus 1 is equal to A sub n, well, let me do this. A sub n plus 2 is equal to A sub n plus 1 plus A sub n for n greater than or equal to 2. So what I'm giving you here is a definition of how you find the numbers within the sequence. All right? Take this back. N greater than or equal to 1. 1. Yeah, sorry, 1. So let's take a look at this formula. I already know what A sub 1 is, right? I know what A sub 2 is. What is A sub 3? Well, according to this, A sub 3 would mean that my n has to be what? For this to be 3, n would have to be 1. Agreed? And I said this formula is good if n is bigger than or equal to 1. Now, according to this, A sub 3 should be equal to what? A sub, remember, n is 1 here, right? Yeah. So this would be A sub 2 plus A sub, n is 1, right? A sub 1. So isn't A sub 3 the sum of the previous two? Like, the third number in the sequence, right here, is these two added, okay, which is 2. Make sense? So how do you get the fourth one? The fourth number in the sequence is the 2 before it. Is the third one plus the second one. So the fourth one is this plus this. Right? You get 3. So the next one is those 2 added. The next one is those 2. So what would the next number in the sequence be? 8 plus 5, which would be 13. Okay? Now, do you see what I mean by like explicit versus this? Like if you wanted to know for this sequence, what's a sub 100? What's the 100th number in the Fibonacci sequence? You would have to know what the 99th and the 98th were, right? But to know the 99th, you have to know the 98th and 97th. But to know the 97th, you have to know the 96th and 95th, right? So you got to go all the way back to the very beginning to 1 and 1 to be able to go out to the end. So it's ugly. Do you all see that? I'm just trying to show you, though, this is an example of a sequence that we cannot come up with a nice, clean, explicit, closed form for. They exist. Those types of sequences exist. We won't mess with those, all right? But they're out there. Now, do you want to know why they call this like the perfect sequence or not? I can show it to you real quick. Do what? It's a perfect what? Oh, perfect weight. Yes, that's it. No, it actually has to do with what's called the golden spiral or the golden ratio. So this is the way it works. I'm going to draw a bunch of squares up on the board right now. Squares have the same side, right? All sides the same. And I'm going to put a number inside of the square. Like if I put the number 1 here, what I want you to understand is that, what I mean by that is that all the lengths of these sides are 1. So either 1 inch or 1 foot or whatever. So that would mean 1. That would mean that this is 2 by 2 by 2 by 2, okay? So I'm going to draw a square now. It's 1, right? I'm going to tell you that. Now, if I draw this square right here, like this, what number do I have to put in there? 1, okay? Now, if I attach a square to the side of those two, like this, I'm telling you it's a square. What number goes in there? 2. Has to, right? Because if that's 1 and 1, then this has to be 2. Now, if I attach a square up here like this, what number has to go in there? 3, right? Because that's 2 and that's 1. So if I attach a square over here, what number has to go in there? 5, 3, 1, 1. So 5. If I go down and over and up, what has to go there? 8. Over here, 13, right? And I keep going all day long, can't I? This would just keep doing this thing all the way around. Now, if we take this and start with our first square, right here, start in this corner, and draw an arc that connects these 2 points, like this, and then an arc going from corner to corner of the second one, then an arc across here, and across here. See how I'm going across the diagonals of each of these boxes? Then we would get this thing called the golden spiral. And what's, I guess, kind of argued, this is debatable, okay? I've seen a lot of different things about this golden spiral. But one of the main arguments or main ideas behind it is that if you look at things in nature, a lot of things in nature follow this sort of pattern. An example is like a seashell. If you've ever looked at like a snail shell, you know, when you look at a shell, it kind of starts with like a tight spiral and then it spirals out like this, right? Yeah. I mean, you could have a spiral that does this. Look at this spiral right here. This spiral, that spiral right there, the distance between each of these spirals is about the same, isn't it? But this, the distance is spreading out as you go. And in the real world, a lot of like snails and shells have a pattern where it spreads out, and they all seem to have this as the pattern. It's like there's a certain ratio that's going on here. It's called the golden ratio, and it's also found in our DNA, the way the helix curves in our DNA, that twist in it is related to this ratio. The way that a plant or a tree grows, the way that the branches are distributed along the trunk is actually some sort of golden spiral. So the Greeks found this a long time ago, and they said, we really like this. And so a lot of their doorways in their buildings were built off of this ratio right here. You know, they didn't build square doorways. They used the golden ratio to build. They thought it was the perfect ratio, so they used it for a lot of their buildings.
Is it the Greeks, right?
The Greeks, yeah. Yeah. So anyway, we could keep going on and on about this, okay? We're going to stop right now, though. All right, so what now? We need to talk about something that some of you may have seen. I'm sure if you took any statistics, you've seen this before. See if you've ever seen that. N factorial. This is called, you would say that N factorial. It's not just you yelling the letter N, okay? N. Okay, that symbol actually means something. I don't really like the way I wrote that. I'm going to make that N bigger, okay? So N with the exclamation point next to it actually means something mathematically. So I'll give you some examples of what it is. So if I write 5 with an exclamation point next to it, what I mean is you start with 5, then you multiply it times 4, then times 3, then times 2, then times 1. So you just start at 5 and just start going down by 1 each time until you get to 1. So what is that equal to? You'd have to multiply these, right? 20 times 3, 60 times 2, 120. Okay? What? Explain what, me multiplying, or?
What is that explanation?
I'm telling you what it is. I'm telling you what this exclamation means. This exclamation means you start at 5, then you reduce the number by 1 all the way until you get down to 1, and then you multiply them all out. So it's a new notation. If I write 8 factorial, then I want you to do 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That's what it would mean. So it's a condensed way of writing this multiplication. All right? So in general, when I write n factorial down, what I mean is I start with n, right? And then I multiply that by what? 1 less than that, right? So I can write that in parentheses n minus 1. And then I multiply that by what? Subtract 1 again, n minus 2. And then I keep doing that until I get all the way down to what? 1, right? I do it all the way till I get down to 1. That's the definition of n factorial right there. And this formula is good